This is the University of Nebraska-Lincoln Design Build Fly team presenting on our aircraft Bliss. First, we'll go over the overall dimensions of the aircraft. We utilized the full span of 60 inches for our wing and chose an aspect ratio of 3.6 for a wing area of 1,000 inches squared. The horizontal and vertical stabilizer dimensions are also shown in this table. Our fuselage dimension comes in at a length of 67 3/8 of an inch. The width of our cargo bay, which is the widest point of our fuselage, is 6.5 inches, and the height of our cargo bay is 8 inches. The gross weights are shown below. For mission 1, we expect to be flying at 9.4 pounds, mission 2, 15.5 pounds, mission 3, 10.55 pounds. Here are the trade studies we performed for this aircraft. On the left, we see a trade study that compares different performances for different maneuvers of the aircraft against different aircraft parameters. We took a cross-section of this at a cruise velocity of around 22 meters per second, which is in line with previous aircraft. And from there, we were able to select a thrust-to-weight ratio of about 0.7 and a wing loading of around 35 ounces per square foot. On the right is the result of our score sensitivity, which shows a bias towards either a very large sensor versus numerous very small sensors. We chose to design around a very small sensor and carry a numerous amount of them in mission 2. We believe this would achieve the highest score and is the simplest to design around. Here's the complete assembly. On the left, we see a model constructed in SolidWorks, and on the right is our final construction on our flight day. Here are the overall dimensions and the 3-view drawing that is displayed in our design report. And here are images confirming that our aircraft matches those designs. Our propulsion system, we run on 2 Cobra 3525/12 motors with a KV of 650. Is a 12-inch propeller with a pitch of 6 inches. For each of these, we use a 50-amp electronic speed controller, and we get around 141 ounces of static thrust at max throttle for each of these. These are powered on 2 6S 22.2 volt, 3.3 amp hour LiPo batteries. For our control architecture, we use a servo and connecting rod assembly. The position and throw of these are tuned on site to allow us to have more dynamic response of our aircraft when we actually make it to those flight days. For our deployment mechanism, we use an Arduino-based motor controller to control a DC motor that controls a spool that is connected to our deployment mechanism. We use a FlySky i6X for our actual controller. This is a 6-channel receiver and controller. For our mission configurations, at mission 1, we have an empty cargo bay, and we position our 2 LiPo batteries in the nose cone to get the CG at around the 1/4 chord position. For mission 2, we load the cargo bay with 28 sensors. We similarly put 2 LiPo batteries in the nose cone position to get the CG around the neutral point. And for mission 3, the deployment mechanism is installed into the cargo bay along with the sensor in the rear of the aircraft. 2 LiPo batteries are placed in the nose cone to get the pre-deployed CG at 1/4 of the chord position and the deployed CG at 1/3 of the chord position. This is because our mechanism uses a rigid assembly of telescoping carbon fiber. Because of this, we end up with a changing center of mass during flight, and it's important that during the entire mission profile, the center of mass stays around the neutral point of the aircraft. We achieve this by having the CG slightly farther forward than we would normally have it on pre-deployment, and that allows us to get it in a still stable position after deployment. Our predicted results we expect to be able to get a score of 1 for mission 1, a score of 0.165 for mission 2, and a score of 252 for mission 3. These are, of course, the nominal results and are not normalized off the expected results from other teams. Next, we'll be going into a demonstration of our aircraft that will include a takeoff and landing. We will also show the technical demonstrations for our deployment and recovery mechanism on the ground, as well as our light system. We do not have footage of deployment and recovery in flight due to technical issues on our flight day.
instantly. You put the card in, boom, and when we flew the 60, and